Okay, it's 5:11. We're gonna get started. We got a good spread of what people think a soup is. A lot of people think soup is a drink. I have no personal opinion on this, but I thought it'd be cool to ask. In case you didn't know, Rao is a professor here. He teaches 70 and 270 right now. But I put in 170 for the fun, like the heck of it, you know. You gotta like keep the continuous. Okay. And then it looks like we're gonna do some crazy cool math. So we're gonna skip 3.4, which is fine. It's kind of disgusting. So we'll do 5.2 instead. And yeah, fill in, please. Please fill in. Oh, and before we start, we're gonna start actually looking at responses, but announcements first. We're gonna project 2 was due yesterday, but keep in mind that we have a very generous late policy. So after the set deadline, you have 24 hours to submit something to the autograder, like run the autograder regularly without incurring a penalty. So then after midnight tonight, it's like minus 2% per hour late that you submit. Now, why do we do this? Well, we get a lot of extension requests that are like, I just need one more day to complete this project. And we kind of use this as like an umbrella for all of you guys. You can't do the, I just need one more day scam for like 5 days. But yeah, that's partially why. And also, it's to psychologically trick you guys into like submitting the project earlier. You have to like submit like an explanation note, you know, for submitting for during the slip period. So you gotta we're playing mind games with you guys. Okay. And then homework 2 is going to be released soon. It's percolation, has stuff to do with weighted quick union. Pretty cool.
What?
It's cool stuff. Yeah. You'll learn. You'll learn. And then some notable responses from last discussion. F of x equals minus kx because it's spring. Get it? That was a good one. Okay. And then f of x equals yes if it holds something 70. And then Cauchy and parabola. Those are the winners. Congrats. You don't win anything, but okay. All right. So this is a warm up. Take like 3 minutes. 5:16. So we have this method called F1, and it's iterating through numList.length, and it looks like it's looking for something, right? So if it checks like the element at index j is equal to I, which is something you pass in, you return it, and if you can't find it, you return -1. So what is the worst case runtime of this? So big O. Well, what is the worst case that we could run into?
At the end.
Either it's at the end or it doesn't exist.
No.
Yeah. So if it's at the end, how many elements would we have gone through?
N elements.
N elements, right?
Elements.
So if numList is n elements long, then we'd be O of n. Does that make sense? Because if you can't find the element you're looking for, then you have to go through every single element, and then you can return -1. So then, now here's another question, which is, rewrite this method to improve the runtime. So what other strategy that you may or may have not learned before will give us like a faster runtime for finding an element in a sorted array?
Binary search.
Yeah, binary search. We're not going to rewrite it, but the key idea, the main idea, behind binary search is that you choose in the middle of the set that you are investigating. So what does that mean? If I have a sorted array that looks like this, I'm going to choose this point here, and if it's less than I know that I has to lie somewhere here, right? If it's greater than I, then I know that I has to, oh my god, did I get this mixed up? Okay, if a pivot, if x here, if x is greater than I, then that means I has to lie on this side, right? And then if x is less than I, then I has to lie somewhere here, because we know everything to the right of x is greater than x, and everything to the left of x is less than x. So effectively what you do is you discard like 1/2 of your array every time you look at an element. So we went through this pattern of like what happens when we discard half of our problem. What kind of runtime do you see? Like in every iteration, you basically solve half of your problems. Yeah, it's log. Why? Because like if you have an array of say size 8, You look in the middle, you can discard 4 elements. So now you're left with 4. You look in the middle again, you can discard 2 elements. You look in the middle again, you can discard 1 element. So you only made like 3 iterations total, and you get, which is like log base 2 of 8, 3. Any questions? Okay. So now we get to do a little bit funner, more asymptotics. You'll see that in the past exams you take, there's this style of problem where like we give you F1, F2, F3, and we're like, give us the runtime. So theta notation, by the way, theta. So we can take maybe 5 minutes to think about each of these. I suggest like maybe drawing like the calls that get made. So for example, over here, if you have like n, you know that you're gonna end up making 2 subcalls, like that. Just from like passing in n, because it calls f1 of n over 2 and f1 of n over 2 twice. So pro tip, draw the stack trace, and we'll do, not the stack trace, but like the function call stack. And we'll come back at like 5:25. Alright, how do we feel? Do we feel good? Bad? Asymptotics are hard, I agree. Math is hard. But, okay, are you ready to go over at least F1? Yeah. Okay, so F1, let's draw the tree. So, it looks like at every time I call F1, I'm going to call F1 twice with like the input halved, right? So it's going to look something like, if I draw this out further, n over 4, n over 4, n over 4, n over 4. Yeah? So then, now let's take a look at, basically it's going to go down until you hit like 0, right? You get a bunch of like 0 nodes. That's cool. But when you're approaching these recursive problems, it helps to define first how many layers you have in this tree. So like, what is the height of your tree? What is it here? How many times do we have to call F1 until we get n that's 0? Log n, right? So this is log n layers. And because it's log n layers, well, congrats, now we know how many layers there are. So then, now to find the total runtime, so the total work is the amount of layers you have times your work per layer, right? And that's kind of hard to define, honestly, but in this case, your work per layer, it's not n per layer. It's actually, because the work done per like node is actually theta 1, and that's because we just call like one function that runs in constant time, right? So, like, the work done per node is different from the amount of subcalls you make. So, a node can do some work in some theta n time, and it can also make some number of subcalls. So you should differentiate that. Yeah.
It says that f of x is a function that runs in time linear to size of its node.
No, it says f of n is something that takes constant time. This is, yeah, let f of x be a, that's just like notation, I think. But on your worksheet, it says that f of n is something that takes constant time. So we know that the work is constant. So then going on, now how do we find the amount of work per layer? So the work per layer is the number of nodes per layer, right? The number of like bubbles we have, because each bubble takes constant time. So it's the number of bubbles, number of like nodes. And what is the number of nodes per layer? Layer I. Yeah, it's 2 to the I. So then that means for every layer, we're doing 2 to the I work. So then we get a sum that looks like this. We get a sum that goes from I equals 0 to log n, right, of 2 to the I. I remember we learned in discussion last week that this is actually 2 to the log n plus 1. So it becomes 2 times 2 to the log n, which becomes 2n. So, and this is bounded by theta n. So this math thing I just did, you can work out the geometric series by yourself, but it's like a bounded geometric series. And one thing you can learn about powers of 2 added together is that If you add all the powers of 2 up to a certain I, the sum of that is 2 to the I plus 1 minus 1. So, yeah. And then because we discard all our constants, we're just like, this is bounded within theta n. Does that make sense?
So the work per layer was 2 to the I.
Yes. Work per layer is 2 to the I because at every layer we have 2 to the I nodes. And each node takes constant work. So it's just like 1 times the number of nodes, which is 2 to the I. Any questions? Okay. Let's do the second one. I'm going to have to do some fancy stuff. Okay. Copy. Paste. All right. So the second one. Do we have any takers for what this could be? Guesses.
No more confidence.
No more confidence. Theta of no confidence. Okay. This is wrong, but you have to be confident in your asymptotic bounds. Okay, let's go through it. Let's draw this. Let's draw the tree again. Okay. So when we do n, what are the next calls that f2 makes?
N minus 1.
Right. We get n minus 1, and then we get another n minus 1. Right. So then now let's go down here. We get n minus 2, n minus 2, n minus 2, n minus 2. So we see the same pattern from our first F1, right? Where we're getting, instead here, now we get n layers, but we still get like 2 to the I nodes per like layer. So then this just turns into a sum that's the sum of I equals 0 up to n of 2 to the I, and we know that gives us 2 to the n plus 1 just by the Here, let me do this. N I equals 0 of 2 to the I is 2 to the n plus 1 minus 1. Just understand this because math. We can go through the proof of this again later.
Wait, minus 1?
Yeah.
I don't do that.
Over here? Oh, so like you're summing 2 to the 0 plus 2 to the 1 plus 2 to the 2, right? And then this turns into, this whole sum turns into 2 to the n plus 1 minus 1. This is because math. We can go through this after class if you want. So then this, we get this sum, right? And then what is this bounded by?
2 to the I.
Yeah, so this is 2 to the n. Any questions? Yeah. Wait, do you have a question? No question. Okay. Does anyone have any questions about this?
In a unit test-taking environment, can you just rely on intuition instead of...
On intuition, sure, but intuition might serve you wrong as we get, because like intuition could have already I already saw some exotic things for this one. So yeah, exotic answers. So usually I like doing math firmly because in 170 you have to do math. But you can use intuition, but depends on how familiar you are already with pattern matching and whatnot. But math is the hardcore, the firm way to prove that this is within a bound.
This isn't a huge topic on literature too, right?
Oh no, it is. We love runtime.
Oh no.
So this is a topic. It's gonna have it's gonna be I'd say at least 20% of the exam.
That's it.
So
Graded on.
you're not graded on work usually. You're just graded on the term you get. Okay, third one. Are you ready? Come this way. Please. Oh my god. Okay. Alright. Okay. What do you guys think the runtime for this is? N to the m? Yeah, that's right. Let's go over why. So, again, we're gonna, because this is recursive, it's very, it's just imperative that you, draw the trace. So, if we start with n, comma m, if we start with like n comma m, we know we're gonna make like n of these, right? So like this layer is gonna have n calls to n comma n minus 1, right? So then what we know already is that the depth of this tree is gonna be m, because we terminate when m is less than or equal to 0. And then now we know that every node here is gonna make like n more layers, right? Of like n, m minus 2. This is like n more layers of n, m minus 2. So this is basically a generalized version of like your binary tree, right? Where every layer just has like some branching factor of 2. So like for binary, this is where like n equals 2, right? So then here n is basically what we call a branching factor. Why? Because for every node, you're going to end up making n calls. So you're going to have n branches from your node. So over here, we know this is behavior if this is m tall. This is like 2 to the m, right? So this is just a generalization of that kind of runtime. So it becomes n to the m. Is that intuitive enough? No? Okay. So let's go through it again. Yeah.
Well, you could write the actual summation,
Oh yeah, we could.
and then you can use like the same.
Well, like here, it's you know that at every layer you're gonna have n to the I.
Yeah.
Yeah. So at this layer you have n to the first,
Yeah.
and at this layer you have n squared.
Yeah.
Dot 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 all the way to n to the m, right? So then, if you do the whatchamacallit, if you do the sum of what I equals 0 up to m of n to the I, you get you do the math, and then you get something of like it's like n to the I plus 1 minus.
It's all the same thing, like 2.
Yeah, it's like the same thing.
That makes sense.
So then you get n to the m. Okay. Are we good? Any questions?
Does it just not do work until the
No,
It doesn't return.
yeah. But in this case, it is like counting the number of nodes. So, can we move on to number 3? Okay. We're gonna move on to number 3. Skip number 4. So skip. Let's come back at like 5:42. Are we okay? Is everyone okay?
No.
Yes? No? Okay. I'm gonna hope that everyone's okay. Yeah. Alright. Let's do number 3. Can we do number 1? Do we feel like? Okay. So when we ask for upper and lower bounds, so best and worst case bounds, best is referring to big omega, and worst case is referring to big O. And a really big mistake that people might make is that they might assume that omega is only for some inputs of n, but that's wrong. Omega is still when n goes to infinity, so it's still an asymptotic analysis. So that's just something you should keep in mind. When you're taking big omega and big O, you're still taking n to infinity. Now you're just saying for omega, it has to run for at least this much time, and for big O, this is the worst case. It will have to be either less than or equal to. And then another thing you guys should know is that you only have a big theta when omega equals big O. So when your lower and upper bounds are like on the same class of functions, then you have a type bound called big theta. Okay. So now that we have that, what is the lower bound of what is the lower bound and the upper bound? So it's like omega. And what is big O? What is omega? Any guesses? Okay, sure. What about big O? Okay, sure. Alright, let's figure out why. So,
Oh, are those the right answers?
yes.
Oh, okay. I was like,
But
got it?
let's look at why. So when we have here we have like something here that does like I of work, right? Theta I of work. So when we're doing asymptotic analysis of these big functions, it's most helpful to break it up into blocks of work and then just kind of take the biggest block of work and you're like, that's my asymptotic. So over here, you take big theta of I, right? Because you go from J to I. And then over here, you take, the understanding here is that this is like O of n over 2 layers that are going to like happen. Because you're going to make O of n over 2 recursive calls. And then here, you're going to say, oh, there's going to be O of log n. O of like 2 log n layers here, right? Now, which conditional do we actually care about? We care about the one that's bigger, right? Because sure, you can have like a smaller amount of layers, but we know that like big O or like asymptotically n it will overtake log n. So when you're looking at, that's why when you do like asymptotics, you can like do like n squared plus n is actually like the same as n squared in asymptotic world because you can just sort of discard the n when n gets really large. All right. So let's focus on the O of n over 2 layers. So at first, I is going to be, whatchamacallit? Well, I is going to be n, right? So we're going to have n comma n. And then it's going to branch off into n over 2 comma n. And then n minus 1. My bad. N minus 1 comma n. So we know here there's going to be n over 2 layers, right? And then we know the amount of work done per each layer is just like whatever I is, yeah? So what you get is, the best way to visualize this, I think, which is the series of like n plus n minus 1 plus n minus 2, is to like draw a square. And then like when you do the sum, you're kind of like drawing a triangle up to, this is pretty bad, down here. This is like what your sum looks like, right? Well, a trapezoid?
Yeah.
You get like a funky triangle thing. But this is something that's like a function. It's some portion of the area covered by n, right? So we have like an n by n like grid. And this is some function of n squared. This is some function of like n squared. It's some like constant times n squared. Something fancy, but it's like a function of area. Which means like when you increment n by 1, you don't grow it by 1, you grow it by n, right? Because like it grows like upwards this way. So like area. So then that's why the work done here is n squared by asymptotics. Just, well, my tablet battery is low. That's bad. Okay. Any questions? So visually it might make sense. It also makes sense if you do the sum of like 1 to n. And that's like n times n minus 1 over 2. That's still n squared. So,
That makes sense.
yeah. So yeah, you get n squared and n squared. So notice here we don't really have to worry about this part because the log n factor is going to be kind of just like squished by the n squared factor. So the good thing about asymptotics is that you can make like very, I guess like wide bounds in terms of your analysis. Like they're not asking you to get it to the constant to like the 3rd decimal point. No, you just want like the order of growth. Yeah.
So I have a question. So when you talk about like best case and worst case, like could each of those have their own like omega, theta, big O balance?
Yeah. So this is a little unclear, but in best case and worst case, you could have your own like big O, big omega, and big theta. But also when we ask for, I guess it's the difference between best case and worst case, and also like lower bound and upper bound, I guess. It's just semantically. But here, so they're like syntactically different, but over here they're kind of semantically the same. But this won't be the same for like something like quicksort, which has like an average case and like a worst case, and then you guys find bounds on those runtimes. Yeah. You don't have to understand what I just said, but it'll be covered soon. Okay, let's go here. True or false? If f of n is within big O of n, and g of n is within big theta of n squared, and both functions are non-negative, then this should be big O. Yeah, okay, yeah. Big O of n and big O of n squared, and both functions are non-negative, then g of n minus f of n has to be at least n, some order growth n. Is that true or false? Yes, this is false. Why?
Because g of n can be constant time.
Right, g of n could be something like n, and f of n could be something like n. And then n minus n is like 0. So the reason is because big O is a very wide bound. You're saying worst case is n squared, but it could be anywhere from constant to logarithmic to linear to like n squared, right? So that's why. So then now here when we have a tighter bound, theta, yeah.
Wait, so can we actually do like n minus n equals 0? Or
Yeah,
because
so like,
couldn't they be just multiplied by any constant?
I mean sure, but like you can set f of n and g of n to be 0, right?
Yeah, but it's like
Or you can set like both of these to be n and n, so to be in the same order. And then that in that case you're like bounded by.
yeah, then in that case, couldn't it be in I don't know what's that sigma of n?
But this
They're
is saying
multiplied
this
by
is
different
true for
constants.
like all f and g, right?
No, I was just talking about that choice of f and g in particular.
Oh,
Like,
like here, g of n and
like
n.
picking them both to be n.
Yeah, like you can just define any arbitrary function. But here this is like you get 0 instead of n when you subtract the two. Okay. So then for number 3, you now replace big O with big theta, and what do you get?
Still false. Or is it true?
Is it now true? Yes, it is now true. And the reason for this is because now f of n has to be some function that's in order of growth n. And g of n has to be some function that's in order of growth n squared. So like it's like almost like an equality instead of like a greater than or a less than. So then when you have like n squared minus n, this is still going to be like bounded within big omega of n, right? Because n squared minus n is going to be greater than just n.
Oh, sorry. I saw that as big O.
Ah, it's big omega. Okay. Are we good? So my tips for mastering like asymptotics, you guys should do the guides that are linked on the course website. Those are pretty helpful. But this is something you should grow very comfortable with. Interview questions, they ask you all the time, what's the runtime of this? 170 all the time, what's the runtime of this? And you're like, you have to prove it, and you feel bad. And so it's, yeah. Okay. 4 is kind of a fluffy question, so we're going to skip it. And we're going to go straight to the cool math one. So let's do number 2 together, because I'm going to do some cool math on you guys. So we're going to give a tight theta bound. So we want theta. And process is a method that runs in big theta of n log n. Okay? So like whatever you put in there runs n log n. Like of the size of the inputs. And then if we just draw like the tree, what we get is we get n, and then we get n over 2. This is a very common pattern. And then we get like n over 4, and then n over 4, and then n over 4, n over 4. Again, we get log n layers, just from the previous problems that we've done. But then now we get like some amount of work per layer that's not really that trivial, right? So at the very top, we get n log n. Yeah? Okay. And then now over here, we get like, we we get like n for one node. So for one node, it's n over 2 times n log n over 2. Does that make sense? Because the size of this node's work is n over 2, and we define this function to have runtime theta n log n, so that's runtime theta n over 2 log n. So it might help if we just use like big N instead of like little n. So,
I think you wrote an extra n rather than
oh yeah, it's 1 over, wait. Oh yeah, whoops, sorry. Okay. Yeah, it's n over 2. Are we good now?
Makes more sense.
Okay, but then we have 2 nodes, right? So this just turns into, at layer 2, it just turns into n log n over 2, right? And then you see the pattern for layer 4, or for layer like 3. Let's define our layering system a little better. Okay, so this is layer 0, this is layer 1, this is layer 2. So at layer 1, we get n log n over 2. At layer 2, we get n log n over 4. Does that make sense? Because you have like n over 4 on the outside, but you have 4 of those nodes, so you get n log n over 4. So then we get this really interesting sum, right? We get like n log n plus n log n over 2 plus n log n over 4 plus dot 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 up until like n log n over 2 to the log n.
So
Right.
is that just
Is this just n? No, it's not. Okay, so we get this sum, right? All the way up to like n log n over n, right? Okay. Now, the sum, so we're going to say s of n equals this. And then we're going to say s of n is, well, we can factor out the n, right? So we get log n plus log n over 2 plus log n over 4 plus dot dot dot. Okay? And then it gets better because now we get n times log n. Remember your log rules? What is log n over 2? Plus dot dot dot. Yeah? It's good so far? Okay. Now we go deeper. So n, this is equivalent to log n plus dot 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 plus log n. And then plus, oh, minus, my bad. And then minus log 2 plus log 4 plus dot dot dot, right? So the math gets better. This, remember n, we're only going to do this log n times, right? So this becomes log squared n. Why? Because you're adding log n times. That's the same as log n times log n, which is log squared n. Okay? And then this is the same as 1 plus 2 plus dot 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 plus log n, right? Yeah? Okay. Now, this is roughly equivalent to n times log squared n minus, remember the series that you learned of 1 plus dot 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 to n is like n times n minus 1 over 2. So we're going to say it's roughly log squared n over 2. So over here, we know that,
should be n plus 1.
oh, okay, yeah, n times n plus 1. Why? Because we know that this series is true. And then it gets better because now we just get, this is bounded by big theta of n log squared n. And that is your cool math for the day. Okay. And if you have any questions about how we derive that sum for I, like 2 to the I, we can go over that. Yeah.
Could you actually go over that?
Yeah. Here, let me make a page, because I have time. Bounded geometric. So we have n of I equals 0 of some
That's dynamic programming? Hey, oh baby, see that's not that.
One of them. What? C3PO? No, it's greedy.
Yeah, it's green. Okay, yeah, okay, phew. I was like, what? I'm pretty sure it's just green.
So then we get like, this is just k to the 0 plus k to the 1 plus k squared plus dot 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 plus k to the n equals s of n. And then,
Also log in.
what?
From I 0 to log in.
Huh? Oh no, I'm just deriving the general form. So the general closed form solution for this is k to the 1 plus k squared plus dot 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 plus k to the n plus 1 equals k times s of n. So we agree this is true, right? So now if we do k s of n minus s of n, it's going to give you, like, all these terms cancel out, right?
Yeah.
So then you get k to the n plus 1 minus k 0. So then now you know that, whatchamacallit, s of n is k minus 1, right? So now you know s of n is k to the n plus 1 minus k to the 0 of k minus 1. So in this case, for s of 2, we get s of, for k equals 2,
Yeah.
for k equals 2, we get 2 to the n plus 1 minus 1 over 1. Yeah.